sites will be highly specific to the initially used template. This is a process of, the first one shown is a non-covalent binding process. Supramolecular interaction is used here for imprinting. And in the second case, covalent binding is used for the imprinting process. And after removal of the template, these cavities will be available for specific interaction with the initial template molecule. Here the template molecule is fructosyl valine compound. In addition to organic polymers, even inorganic polymers can be used for molecular imprinting technology. Here silica is used as the imprinting monomer, imprinting polymer, and functionalized silica compounds such as amine functionalized silica is used as the functional monomer, and this particular kind of silica imprinted polymer is used for the sensing of picric acid. Picric acid is a specific pollutant for aquatic life, and so its detection is highly important. And in addition to free radical polymerization, sol-gel method, as already mentioned, there is another technique called electrochemical polymerization, which is very easy to execute for the formation of MIP. Electrochemical polymerization of a variety of monomers are possible, and after removal of the specific template molecule, these cavities can be acting as specific sites for the interaction of those specific molecule or those molecules having a functionalities similar to that. And once we prepare the MIP, it has to be characterized using various methods. I will brief you about some. I am not going into the details, but I will brief you about some of the characterization methods used for the characterization of MIPs. One is elemental analysis, elemental microanalysis. Second one is solid state NMR. These polymers are solids, and so we have to use specific solid state NMR process for their sensing, for their characterization. And third one is FTIR, which can reveal about the specific interactions in the molecule. And the morphology can be analyzed by microscopic methods such as SEM. And the porosity can be analyzed by nitrogen sorption porosimetry, mercury intrusion porosimetry. These are some techniques. We no need to know about the details. And Scatchard analysis is used to analyze the specific interaction of the monomer with the template molecule. And Freundlich and Langmuir isotherms are also used for the adsorption of these molecularly imprinted polymers with a specific template. And for every applications of MIPs, the first process is adsorption. After adsorption, it's selective sensing, or it's selective catalysis, or it's selective any other applications, separation such as separation, etc. will be possible. So first thing in MIP polymer application is the adsorption of a specific target template molecule. And the advantages of MIP are high selectivity, because we are imprinting with a specific template molecule. So after the imprinting technique, the polymer can only specifically sense or selectively sense that specific template molecule. For example, if we use it for the sensing of a molecule such as dopamine. Dopamine is a chemical which is responsible for the disease such as Parkinson's disease. So its detection in body fluids such as blood and urine is highly important. But when we analyze the dopamine in a urine sample, there will be definitely presence of uric acid and also ascorbic acid. So our sensor should sense specifically dopamine. Instead of sensing specifically dopamine, if it senses the molecules present in the urine content, the results will be wrong. So if we use a sensor material which can specifically interact with the dopamine, it can specifically sense that molecule only. So for selective sensing, MIP process is highly advantageous. And in MIP, there will be high affinity for the target molecule. And compared to this, high affinity is mentioned compared to even with the biological systems such as proteins, nucleic acids, etc. And another advantage in comparison with the biological systems such as proteins, nucleic acid, etc., is the high physical robustness and strength of the polymer. So instead of using some enzymes from the human beings or from any organisms, the use of imprinted polymer will be highly beneficial because the polymer have high physical robustness and strength, and it is resistant to elevated temperature and pressure. We know that enzymes cannot survive high temperature. Even at 70 degrees Celsius, some of the enzymes get spoiled. But instead of that, these MIPs can resist elevated temperatures and pressures, and also it is inert towards acids, bases, metal ions, and organic solvents. And comparatively, compared to the cost of an enzyme or a biological system, the cost of MIP is very low. And the lifetime of these molecularly imprinted polymers is very high. We can even store the MIPs for several years at room temperature. And we already mentioned about the application areas of MIPs. I am just mentioning and showing some of the applications. It is widely used in separation and purification, separation of a specific molecule from a mixture of molecules, or purification of a specific molecule from a mixture. And for chemical sensors, as I mentioned now, and for catalysis, it can be for enhancing the rate of reaction by binding with the substrate molecule, for the selective adsorption of the adsorption of the substrate and its proper orientation for catalysis, or for the production of a specific transition state, or for the production of a specific product. And these MIPs are also used in drug delivery, and they are also used as biological antibodies and receptor systems. About the use of MIPs in separation techniques. We know that chromatography is an advanced separation technique, and we can use MIPs in chromatographic columns for the specific identification. Even chiral molecules can be specifically adsorbed on the highly specified MIP incorporated columns, such as in HPLC, high performance liquid chromatography, and also we can use GC columns, but where the gaseous molecules has to be sensed. And it is mostly used in liquid chromatography. And we can use non-covalent imprinting procedure or also covalent imprinting procedure for preparation of liquid chromatography columns for the separation process. And the drawbacks of this technique, MIP technique, is the excessive peak tailoring in the chromatogram and the broadening of peaks, but these can be avoided by using covalently imprinted, molecularly imprinted polymers. These are the solidifiers extraction. The figure shows the extraction of a specific molecule, pentadiamidine. Here the column is having spheres with the predetermined sites for pentamidine drug. So all molecules will flow very fast except the pentamidine. It will be selectively adsorbed on the column. And by using a specific solvent, after the set of all other components, by using a specific solvent, we can elute the specific molecule. So separation is 100% pure. This is the merit of this method. This method of solid phase extraction. It is called as MISPE. And this is the MISPE for the detection of chromatogram for the detection of 1-methyl adenosine. Here, the third one is the spiked MISPE, the molecularly imprinted spiked material is used for selective separation or sensing, and in the case of C, only that molecule is sensed. That is there is no other peaks available, so that is the advantage of this method. And there are several studies applying imprinting technology to different selection extraction techniques. I am not going into the details of these techniques. And the second application I mentioned is about the use of MIPs as chemical sensors and also as biological sensors, biosensors. The importance of biosensors are that we have to selectively sense a specific molecule from a mixture. So We cannot use a normal sensor, or the normal sensor may not be highly specific or selective. So by imprinting the target molecule initially, we can improve the selectivity. These sensors can be widely applied in environmental analysis as well as for the detection of adulterants in drugs and for in foods, and for the clinical diagnosis of certain diseases by detection of the presence of certain chemicals. These MAPs can be on monoliths or also as layers or thin films. And the sensing may be by detecting the signals. It can be a electrochemical signal such as increase in current, change in voltage, etc., or increase in resistance, or it can be an optical sensing, and it can also be piezoelectric. We are more interested in the electrochemical sensing using particular molecule. MIPs are also used in catalysis. I already mentioned about the specific binding with the substrate molecule or with the transition state or with the products. So we can improve the rate of catalysis or rate of reaction, and also improve the product selectivity by using MIPs in catalysis. The additional advantages is that we can use elevated temperature and pressure for the process. We can use acidic solution or basic and everything. Even enzymes are used, or the imprinted enzymes, immobilized enzymes are used in many catalytic process. But the error is that we have to choose room temperature and atmospheric conditions, pressure conditions for the catalysis. We cannot use any acids or bases that badly affects the enzyme. So in comparison, MIPs are promising candidates in catalysis. This is a dehydrohalogenation reaction using functional monomer immobilized molecularly imprinted polymer, and it can be used for the selective sensing of the specific substrate molecule, and since the orientation is correct, we can specifically lead to the formation of a specific product. For example, here the trans product is formed in large amount. There is no cis product formation. And the use of MIPs in drug delivery. Drug delivery and drug release are some terms nowadays used specifically about drugs, because usually for applications, if we are inhaling a medicine such as paracetamol, it will be released in large amount to the non-specifically to everyone. So its application to the target point will be, the concentration will be minimum because it is spreading to everywhere, and so its application is it will not be so effective, but instead it will affect all organisms in the body. So drug delivery should be highly specific, and the drug release should be sustainable. Slow release is required, because if we are consuming a drug for 24 hours, after a 24-hour gap, we will consume the next drug. So the first drug should be released slowly, and it will last for 24 hours. And for cancer treatment, etc., the drug release may be for chemo, etc. Drug release should be very slow. Maybe we are taking the chemo injection after 2 weeks. So the drug already injected should be released within 2 weeks. And also it should be released to that specific site, because these drugs will be destroying the cells. So if the drug goes everywhere in the body, it will destroy all the cells. This is why most of the cancer patients are very weak during the chemotherapy process. But if the drug delivery is only to the cancer sites, it will not affect the health of the person. So drug delivery is an important process, and its sustainable release is another matter. And there are lots of work using imprinted polymers for the drug delivery process, because if we are using the cancer sites are highly specific, because the cancer cells, in the cancer cells there will be availability or presence of certain chemicals. For example, hydrogen peroxide should be present in cancer cells in high quantity, but in normal cells it will not be present. So if our drug delivery medium is highly specific to the radicals, it will release the drug onto those sites only. So if we design a particular drug delivery system like that, here for the release of a particular molecule, for the release of a particular testosterone drug, the concentration of hydrocortisone in the medium is effective because the drug release medium is prepared using an MIP with hydrocortisone. So if there is a hydrocortisone molecule in the medium, the MIP will specifically bind with that and it will slowly release the testosterone. We can design such drug delivery systems for highly specific applications and for highly specific targets. It is schematically shown here. And most of the applications of molecularly imprinted polymers is environmental applications for the detection of pollutants and also for the detection of adulterants. Even most of the sensing is based on these environmental applications. So the merit of molecularly imprinted polymers are high selectivity, high sensitivity, ease of preparation and low cost. But there are many drawbacks to this MIP process. So here we are imprinting molecular, we are preparing MIPs in the presence of carbon nanostructures. Why we need carbon nanostructures on MIP? I already mentioned that our specific interest is on electrochemical sensors. So the material should be sensing electrochemically. So its conductivity, electron mobility and electrocatalytic activity, everything is important. But MIPs lack conductivity. And thus it is of, if we are using a conducting polymer, it will be conducting, but it may not be a best MIP. So we have to use all polymers for this imprinting process, but normally most of them will not be conducting. So here we are adding some conducting additives such as carbon nanostructures for improving the performance of MIPs. So it will improve the electrocatalytic activity. Lack of conductivity limit their application in electrochemical sensors. So by the incorporation of carbon nanostructures, we can improve the performance of MIP sensors. Usually carbon nanostructures such as carbon nanotubes, graphene, carbon or graphene quantum dots, fullerene, etc. for this purpose. And compared to the other materials, graphene prepared via specific routes and graphene quantum dots are cost effective. So we are specifically concentrating on graphene as a carbon nanostructure for preparing MIPs. Not for preparing MIPs, for preparing carbon nanostructure incorporated MIPs. Because we are mainly focusing on electrochemical sensing of pollutants or any other adulterants, etc., or for biological molecules such as dopamine, etc. And in electrochemical sensing, we are sensing via signals. If there is an oxidation occurring to the sensor molecule, there will be a large change in the current. So we have to detect the output signal. So to monitor the current change, etc., our conducting or our electrode should be conducting. That is why we are incorporating carbon nanostructures for improving the performance of MIPs. I am briefing you about the carbon nanostructures. We know there are lots of carbon nanostructures such as fullerene, carbon nanotube, graphene, etc. And I am sticking on graphene. And for your knowledge, most of you may know, there is a new carbon allotrope called cyclocarbon C18. It is with alternate single bond and double bond. It is invented in 2019. Theoretically predicted a few years back, maybe about 30 years back, but it is experimentally prepared in 2019. This cyclocarbon C18. I am interested more about graphene and we are sticking on graphene. The carbon nanostructures can be applied in various fields like MIPs, and I think the application of carbon nanostructures are more. Carbon nanostructures can be carbon nanofibers, graphene, carbon dot or graphene quantum dot, carbon nanotubes, graphene, fullerene, etc. Okay. And combining MIPs with carbon nanostructures has various applications, taking the advantage of both the materials. So they can be applied in trace detection of analytes in biological fluids. For the detection of high concentration of materials, we can use many various techniques. But for the analytes in biological fluids, the presence may be in, say, nanomolar level. For those detection, you have to use specific materials. Here comes the importance of carbon nanostructure incorporated MIPs. And it is also used in biomedical analysis of analyte, diagnosis of disease, because disease sites will be having the presence of some specific molecules, and by analyzing the specific molecule, we can detect the or diagnose the disease. And it can be also used for fluorescent biosensors and for clinical detection of analyte and biomarker for diagnosis of diseases, and it is also used for optical sensors. So the presence of carbonaceous materials on MIP improves their selectivity and sensitivity, and also the linear range of detection. We can start from even from picomolar level to till molar level by the incorporation of carbon nanostructures. In the electrochemical sensors, the sensing is done using some electrochemical techniques such as cyclic voltammetry, square wave voltammetry, DPV, differential pulse voltammetry, amperometry, etc. In most of the cases, at a specific voltage, there will be a change in current if that specific molecule is present. And the selectivity in sensing is highly important. So at a specific voltage, only one molecule should be sensed. Then only the electrochemical sensor will be successful for the selective detection. About nanocarbon-based MIP electrochemical sensors, I already mentioned about the carbon materials such as graphene quantum dot, graphene, fullerene nanotubes, and here the MIP preparation occurs in the presence of monomer as well as specific targeted template molecule and carbon nanostructure. The resultant is greater conductivity, high sensitivity, high selectivity, and good analytical performance. And these carbon nanostructures can be prepared via two methods. Either top-down method by cutting of bulk carbon materials to nanocarbon. For example, cutting of graphitic layers to graphene. Or bottom-up method by the use of precursor molecules such as glucose, etc., and polymerizing them to the specified carbon nanostructure such as graphene quantum dot, graphene, etc. So both top-down methods as well as bottom-up methods are there. And for the graphene quantum dot preparation, the environmentally benign methods are bottom-up methods such as micropyrolysis, hydrothermal synthesis, electrochemical method, etc. And there are other methods of preparation such as hydrothermal process. I am not going into the details. And this is the MIP preparation in the presence of carbon dot. Here the functional monomer is VPBA. This is a styrene functionalized with boronic acid. And these sites can be specifically bind with the glucose molecule. And then polymerization of the polystyrene polymerization of the styrene site occurs, and in the presence of carbon dot. So polymerization occurs on the carbon dot, and it will be embedded with the glucose molecules. Then we are removing the glucose molecule. So there will be cavities which can specifically bind with the glucose molecule. So MIP preparation in the presence of carbon nanostructures will not require any other steps. During the polymerization step, we have to use the carbon nanostructure. That is the only extra requirement. This is the MIP preparation in the presence of carbon nanotubes. And this is the MIP preparation in the presence of graphene as well as polyaniline. It is a conducting polymer of aniline. And it is used specifically for the detection of picric acid. Picric acid is a targeted pollutant of aquatic medium. Here, the picric acid molecule is specifically binded with the polyaniline. So after picric acid removal, if there is a mixture carrying picric acid, it will selectively sense that molecule. So The applications are in pesticide detection, toxin detection, uh, anion detection such as for the detection of nitrate etc. and for the detection of antibiotics. Antibiotic detection is highly important because after the consumption of antibiotics, a large quantity of antibiotics are secreted. And for example, if we give an antibiotic to a cow, it will be going to fields and it will be secreting there. So the water medium there will be contaminated. It will go to rivers, etc. So the presence of antibiotics will be there in the river water, but it will be in low quantity because it is mixed with river water. So its presence will be in low quantity. So these specific antibiotic in a low concentration cannot kill a bacteria, but it can lead to the formation of antibiotic resistant bacteria. So the detection of presence of antibiotics in water is highly important. And the sensing of antibiotics can be also performed using molecularly imprinted polymers. Here there is a polymer imprinted on carbon nanotube and RGO. It is specifically used for the detection of antibiotics. And in addition, it can be these carbon nanostructure based MIPs can be used for gas sensors such as ammonia, NO2, H2S, for biological sensor of specific molecules, humidity sensor, and also for pollutant sensors, for specific chemicals in fish, adulterants in fish, for example, ammonia, etc., and also for the sensing of heavy metals such as mercury, lead, etc., and for the detection of ammonia in, I already mentioned it, and these sensors can also be mechanical sensors. And our study of interest is on the chemical detection of the following molecules: tetracycline, dopamine, rutin, norfloxacin, 4-nitrophenol, which is a aquatic pollutant. The other rutin and norfloxacin are drugs, heavy metals. Chlorophenol, it is a pollutant. Uric acid, it is for the analysis of a specific disease. Glucose, for detection of diabetes. Metamizole, etc. And dopamine. And the challenge only using graphene or a carbon nanostructure is only in the selective sensing of this material. The graphenes can be acting as a sensitive, and it can even sense from the picomolar level or nanomolar level, but it cannot selectively sense a specific molecule always. So by modifying carbon nanostructure with MIP, the selectivity can be highly improved. And about some of the commercial preparation of graphene, I am not going to the details, just mentioning because our time is 11:55 now. Graphene can be prepared via various means. It can be prepared via exfoliation of graphite, intercalation of other materials to the graphitic layers and further exfoliation, by arc discharge, by chemical vapor deposition, silicon carbide heating, heating of solid carbon sources such as glucose, and reduction of graphene oxide, and also by opening up of or unzipping of carbon nanotubes. The techniques are shown here. But commercially, graphene is prepared via graphite oxide assisted route. The route is shown here. Graphite is subjected to drastic oxidizing conditions, and oxygen moieties are incorporated between the graphitic layers, and further sonication, ultrasonication leads to the formation of graphene oxide. But for electronic applications, we need an extended aromatic conjugative network for electronic mobility. So we have to reduce the graphene oxide to form reduced graphene oxide. These materials are not called as graphene, but only as reduced graphene oxide materials, because some of the oxygen moieties still remain on the matrix. So it will not be apt for electronic applications. We have to get the perfect aromatic network. This is one of the problem of the graphite oxide method, but it can be used in catalysis or any other applications. And another issue graphite oxide assisted method is we are using drastic oxidizing conditions for the preparation. A large amount of fumes are originating here. It is corroding and not an eco-friendly method. These are the photographs taken during the preparation of graphene oxide from our lab. These are various steps. We are doing the synthesis at low temperatures. Still there are lots of fumes coming. So it is not an eco-friendly method. So the limitation of graphite oxide route is the preparation in a hazardous condition, and in addition, the graphene sheets prepared here is not perfect. there are lots of defects and functionalities on the graphene sheets. The entire process is time consuming and laborious. Time consuming is okay, but it is laborious too. And sometimes the thickness control of the produced graphene or reduced graphene oxide is not so promising as the highly costly methods such as epitaxial graphene growth or CVD process, but we cannot prefer these methods due to the costly procedures. So, since we are sticking on the environmental applications, we have to prepare graphene via green methods. And for an commercial application, it should be cost effective too. So, I will mention you briefly about some of the cost effective methods which are developed in our laboratory for the preparation of graphene. The Nobel Prize winning method for the preparation of graphene is by mechanical cleavage. We are taking graphite and taking on a scotch tape having gum on both sides. We are repeatedly peeling off graphite. Layers are separated, and from 1,000 layers, and in a later stage, we will get a single layer. But the process is highly laborious. We have to spend a lot of time for the preparation of a single layer. Sometimes it should be cracked too. So this is maybe the Nobel Prize winning method for the production of graphene, which is it cannot be applied commercially. Another method is sonication, but the issue is that sometimes we have to use toxic solvents such as DMP, NMP, N-methyl pyrrolidine, dimethyl formamide for the exfoliation of graphitic layers. One of the cost-effective method is ball milling. And if we are using liquid phase sonication with the help of any eco-friendly solvents such as water, alcohol, medium, etc., the method is friendly. Another method is ball milling. We can produce few layer graphene easily with ball milling with any other materials or with graphite. And another method is IC, interlayer catalytic exfoliation. Here the method is shown here. We are incorporating other species between the layers, and then it is easy to exfoliate graphene. This is the process of ball milling. Balls are continuously moving and the mill is also moving, and as a result the milling agents goes between the layers of graphene via non-covalent interactions, and the graphene layers are separated. Another issue is that the layers are somewhat fragmented too, but the well exfoliation is possible if we choose specific exfoliating agents. These exfoliating agents can be in liquid medium as well as in solid medium. And the exfoliating agent is not so costly. Even we can use glucose for the exfoliation of graphitic layers. We have reported a glucose-assisted method for the preparation of green graphene. Both calcination after ball milling process, by calcination we are getting graphene, and also by liquid method we can get aqueous processable graphene. This is the process for the production of graphene. This is the initial graphite taken. This is the photograph of sugar taken. We mix both, and after 2-hour ball milling, the volume expansion is there. By 10-hour, volume expansion is increased, and after 30-hour, the volume is almost doubled. And calcination, the graphene volume is shown here, and the initially taken graphite is shown in the bottle. It is only a very low amount. The graphite layers are exfoliated and the volume is expanded. This prepared graphene is dispersible in a variety of solvents, organic solvents, and it is hydrophobic in nature too. These are some of the characterization techniques of the prepared graphene. I am not going into the details. This work is published in the New Journal of Chemistry of RSC. This method is extended for the preparation of aqueous graphene, aqueous processable, water processable graphene. One of the major limitation of the graphene prepared via other methods than graphene oxide is that they are aqueous processable nature. But this graphene can be processed in aqueous medium, and large number of other species such as metal oxides can be easily incorporated to graphene for forming nanocomposites. Second one is liquid phase exfoliation. We have used here a mixture of isopropyl alcohol and water for the exfoliation of graphite, and further magnetization is used using iron compound, and we have prepared a magnetic graphene nanocomposite. I am not going into the details because time is almost 12. This work is also published in a journal of solid state chemistry. And we can use the assistance of surfactants to improve the yield of graphene. And this type of graphene is also prepared by us. And this is a work used for the preparation of graphene for the selective sensing of ammonia. We can see that in the presence of ethanol, NO2, acetone, isopropyl alcohol, H2S, etc., ammonia is sensed in a selective manner. If we can incorporate, here the material is ion incorporated graphene only, and if there is an MIP also, the sensing will be, the selectivity will be further improved. This work is published in the journal Applied Surface Science. And next about the intercalation exfoliation of graphite. Actually, we started this work in the year 2016, and the paper got acceptance today morning, early morning. So it is a fight for 4 years. But the graphene prepared, the best graphene prepared in our laboratory is this one. Sometimes it will take time to get recognition. And here we could prepare ion incorporated graphene layers. The advantage is that the prepared graphene is not having any defects. If there is a peak here, I think you can see the peak here around 1300. And if there is a peak here, the graphene will be of defective nature. But our prepared graphene is not having any defect in the graphene sheet. So it will be having a perfect aromatic network, and it is highly applicable for electronic application such as in electrochemical sensors, supercapacitors, etc. We have performed the supercapacitor applications of this material, and we got a outstanding result for the material, and the supercapacitor retained more than 50% of its activity after repeated charging and discharging for 10,000 cycles. So the material is highly promising. The paper is accepted in the Journal of Energy. And here is some of the references of the work. I would like to acknowledge my students, Dr. Soumya B. and Vijayashree Haridas, who are working in graphene. And the graphite oxide assisted method is mostly tried by my student, Dr. Divya. She is working in the Malappuram Government College, Women's College. And I also thank my research scholars and my college and University of Calicut, and all the head and faculty members of the department, principal of our college, different funding agencies for analysis support as well as for instrumental support, and STIC for analytical support. This is my current research group. Ms. Remani Casey is already submitted their thesis, and 3 of them are doing PhD, and 1 more is joined now. And I just mentioned about the student fellowship available for those who are interested to do research. They are UGC, JRF or SRF. JRF will be converted after 2 years to SRF. SRF means Senior Research Fellowship. And for OBC candidates, UGC Maulana Azad National Fellowship is there for Muslim candidates. And E-Grants is there for Scheduled Castes candidates. And KCST Research Fellowship is there for candidates qualifying KCST written test and interview. And the fellowship amount is same as that of UGC JRF. The current amount is in Pattambi they are receiving 31,000, and the fellowship is 31,000. And the difference only in the HRA house rent allowance in Pattambi it is 2,480. So for doing research, you are getting just like a salary you can earn, and also just like a job, but different from a job, we can enjoy the research. These are my students who had completed their research: Dr. Venu Vivi, Dr. Sutta Casey, Dr. Divya P. and Soumya B. And Dr. Silija PB, PP was our UGC postdoctoral fellow for 5 years. Now it is open for any discussion or questions you may ask. I think the presentation was clear to you. Hello.
Hello.
Teacher, yes.
Hello.
Yes, can hear you.
Thank you, Vinita. Hello. Hello.
Was it audible to you?
Yes.
Yes. Can
A
hear you.
few times the audio was not very much audible in between.
Sorry. I didn't see the screen because you are
Most of the time it was okay. Most of the time it was okay.
okay. Okay. Thank you. The students can ask any questions now. You can interact freely. You can ask in Malayalam too.
Any questions? Hari, any questions
You
in
can clear
YouTube
your
channel?
doubts.
Hello. Hello. Any questions in YouTube channel? Okay, I think there are no questions. Hello.
Is it because you are not audible? Okay, anyway, thank you.
Hello. Hello. Lindsay. Hello, Lindsay. Okay, I think there is no question in the YouTube channel also. There are no questions now. I think it is all clear for them.
Okay.
Now I invite Aisha Shiril, our BSc student, for the formal vote of thanks. Aisha?
Hello, am I
Hello.
audible?
Yes.
Good morning. Honorable dignitaries, distinguished guests, respected teachers, and their participants. On the behalf of Majlis Arts and Science College, its entire fraternity, and the organizing committee, I feel immense pleasure to take this opportunity to propose a vote of thanks to our eminent speaker, Dr. Binida Ma'am, Assistant Professor, Department of Chemistry, SNGS College, Patangi, who spared the time from her busy schedule to grace this webinar with extremely relevant address on molecularly imprinted polymer incorporated nanocarbon-based materials for versatile application. Thank you, Veda ma'am, for explaining and demonstrating what is imprinting and how MIPs are produced, their applications in various fields, chemical characterization and their advantages, especially their applications drug delivery, electrochemical sensing, etc. She also explained how molecularly imprinted polymer matrix can be used for environmental pollution analysis, then adulteration in food materials, etc. And also, I would like to take this opportunity to place on award our heartily, reward our heartily thanks to Shantakumari ma'am, head of Department of Chemistry, Majlis Arts and Science College, for the support and guidance she has extended to all of us. I also extend my sincere thanks to Lindsay ma'am, Assistant Professor, Department of Chemistry, and Deepak sir, Assistant Professor of Department of Chemistry, Majlis Arts and Science College, for the enormous cooperation in the organization of this session. Also, a big thank you to all the one who worked behind for arranging such an informative event session. We have been very fortunate enough to be backed by a team of very motivated and dedicated faculty members of the postgraduate department of chemistry, Majlis Arts and Science College. Last but not the least, my deep appreciation and thanks to all the delegates who chose to be online with us and attended the webinar with great enthusiasm and made it a successful one. Once again, I thank all of you for being with us in the session. Thank you very much and have a nice day.
Thank you, Aisha. I think we can conclude the seminar. Thank you, Binda, for your very informative presentation. Interesting also because it was concerned about eco-friendly materials for detection of adulteration, pollution, environmental pollution, etc. Then drug delivery. Everything was very interesting. Thank you very much. Thank you.
Thank you, ma'am. Thank you, ma'am. Thank you all.
Hari Mohan, Lindsay. Okay. I think some problem is there. Nobody from the department is responding. Drashya?
അവിടെ എന്തോ നെറ്റ്വർക്കിന് എന്തോ പ്രശ്നം തോന്നുന്നു. കിട്ടുന്നില്ല, അവരൊക്കെ കിട്ടുന്നില്ല.
Shall we conclude?
Yes, ma'am. Yes, we can conclude now.
Okay, we can conclude. Thank you.
Okay, thank you.
Thank you all the delegates. The feedback form is there.